Global warming potential, GWP, is a measure of how much heat a greenhouse gas traps in the atmosphere over a specific time period relative to carbon dioxide, CO2 2232. It is expressed as a multiple of warming caused by the same mass of CO2. Therefore, by definition, CO2 has a GWP of 1. For other gases, it depends on how strongly the gas absorbs thermal radiation, how quickly the gas leaves the atmosphere, and the time frame considered. For example, methane has a GWP over 20 years GWP 20 of 81.22, meaning that a leak of a ton of methane is equivalent to emitting 81.2 tons of carbon dioxide measured over 20 years. As methane has a much shorter atmospheric lifetime than carbon dioxide, its GWP is much less over longer time periods, with a GWP 100 of 27.9 and a GWP 500 of 7.95. 7 sm to 24. The carbon dioxide equivalent CO2e or CO2eq or CO2e or CO2eq can be calculated from the GWP. For any gas, it is the mass of CO2 that would warm the Earth as much as the mass of that gas. Thus, it provides a common scale for measuring the climate effects of different gases. It is calculated as GWP times mass of the other gas. Definition: the global warming potential, GWP, is defined as an index measuring the radiative forcing following an emission of a unit mass of a given substance accumulated over a chosen time horizon relative to that of the reference substance, carbon dioxide. The GWP thus represents the combined effect of the differing times these substances remain in the atmosphere and their effectiveness in causing radiative forcing. 2232. In turn, radiative forcing is a scientific concept used to quantify and compare the external drivers of change to Earth's energy balance. 1 to 4 radiative forcing is the change in energy flux in the atmosphere caused by natural or anthropogenic factors of climate change as measured in watts per meter squared. As governments develop policies to combat emissions from high GWP sources, policymakers have chosen to use the 100-year GWP scale as the standard in international agreements. The Kigali Amendment to the Montreal Protocol sets the global phase down of hydrofluorocarbons, HFCs, a group of high GWP compounds. It requires countries to use a set of GWP 100 values equal to those published in the IPCC's Fourth Assessment Report, AR45. This allows policymakers to have one standard for comparison instead of changing GWP values in new assessment reports. 6. One exception to the GWP 100 standard exists. New York State's Climate Leadership and Community Protection Act requires the use of GWP 20, despite being a different standard from all other countries participating in phase downs of HFCs. Calculated values. The global warming potential, GWP, depends on both the efficiency of the molecule as a greenhouse gas and its atmospheric lifetime. GWP is measured relative to the same mass of CO2 and evaluated for a specific timescale. 8. Thus, if a gas has a high positive radiative forcing but also a short lifetime, it will have a large GWP on a 20-year scale but a small one on a 100-year scale. Conversely, if a molecule has a longer atmospheric lifetime than CO2, its GWP will increase when the time scale is considered. Carbon dioxide is defined to have a GWP of 1 over all time periods. Methane has an atmospheric lifetime of 2 years. 9. Table 7.15. The 2021 IPCC report lists the GWP as 83 over a time scale of 20 years, 30 over 100 years, and 10 over 500 years. 9. Table 7. At longer time, the decrease in GWP at longer times is because methane decomposes to water and CO2 through chemical reactions in the atmosphere. Similarly, the third most important GHG, nitrous oxide, N2O, is a common gas emitted through the denitrification part of the nitrogen cycle. 10. It has a lifetime of 109 years and an even higher GWP level running at 273 over 20 and 100 years. Examples of the atmospheric lifetime in GWP relative to CO2 for several greenhouse gases are given in the following table. Formula. Years 9, Table 7.1511. WM2 ppb1 molar basis. 9, Table 7.511. Estimates of GWP values over 20, 100, and 500 years are periodically compiled and revised in reports from the Intergovernmental Panel on Climate Change. The most recent report is the IPCC 6th Assessment Report Working Group I from 2023. The IPCC lists many other substances not shown here. 13, 9, 14. Some have high GWP, but only a low concentration in the atmosphere. The values given in the table assume the same mass of compound as analyzed. Different ratios will result from the conversion of one substance to another. For instance, burning methane to carbon dioxide would reduce the global warming impact, but by a smaller factor than 25, because the mass of methane burned is less than the mass of carbon dioxide released. Ratio 1.7415 for a starting amount of 1 ton of methane, which has a GWP of 25. After combustion, there would be 2.74 tons of CO2, each ton of which has a GWP of 1. This is a net reduction of 22.26 tons of GWP, reducing the global warming effect by a ratio of 2.74, approximately 9 times. The values provided in the table below are from 2007 when they were published in the IPCC 4th Assessment Report. 2218, these values are still used as of 2020 for some comparisons. A substance's GWP depends on the number of years denoted by a subscript over which the potential is calculated. A gas which is quickly removed from the atmosphere may initially have a large effect, but for longer time periods, as it has been removed, it becomes less important. Thus, methane has a potential of 25 over 100 years, GWP 100 equal to 25, but 86 over 20 years, GWP 20 equal to 86. Conversely, sulfur hexafluoride has a GWP of 22,800 over 100 years, but 16,300 over 20 years, IPCC 3rd Assessment Report. The GWP value depends on how the gas concentration decays over time in the atmosphere. This is often not precisely known, and hence the values should not be considered exact. For this reason, when quoting a GWP, it is important to give a reference to the calculation. The GWP for a mixture of gases can be obtained from the mass fraction weighted average of the GWPs of the individual gases. 24. Commonly, a time horizon of 100 years is used by regulators. Water vapor does contribute to anthropogenic global warming, but as the GWP is defined, it is negligible for water. An estimate gives a 100-year GWP between 0.001 and 0.0005. Water can function as a greenhouse gas because it has a profound infrared absorption spectrum with more and broader absorption bands than CO2. Its concentration in the atmosphere is limited by air temperature, so that radiative forcing by water vapor increases with global warming positive feedback. But the GWP definition excludes indirect effects. GWP definition is also based on emissions, and anthropogenic emissions of water vapor, cooling towers, irrigation are removed via precipitation within weeks, so its GWP is negligible. Calculation methods. When calculating the GWP of a greenhouse gas, the value depends on the following factors: the absorption of infrared radiation by the given gas, the time horizon of interest integration period, the atmospheric lifetime of the gas. A high GWP correlates with a large infrared absorption and a long atmospheric lifetime. The dependence of GWP on the wavelength of absorption is more complicated. Even if a gas absorbs radiation efficiently at a certain wavelength, this may not affect its GWP much if the atmosphere already absorbs most radiation at that wavelength. A gas has the most effect if it absorbs in a window of wavelengths where the atmosphere is fairly transparent. The dependence of GWP as a function of wavelength has been found empirically and published as a graph. Because the GWP of a greenhouse gas depends directly on its infrared spectrum, the use of infrared spectroscopy to study greenhouse gases is centrally important in the effort to understand the impact of human activities on global climate change. Just as radiative forcing provides a simplified means of comparing the various factors that are believed to influence the climate system to one another, global warming potentials, GWPs, are one type of simplified index based upon radiative properties that can be used to estimate the potential future impacts of emissions of different gases upon the climate system in a relative sense. GWP is based on a number of factors, including the radiative efficiency, infrared absorbing ability of each gas relative to that of carbon dioxide, as well as the decay rate of each gas, the amount removed from the atmosphere over a given number of years relative to that of carbon dioxide. The radiative forcing capacity, RF, is the amount of energy per unit area, per unit time, absorbed by the greenhouse gas that would otherwise be lost to space. It can be expressed by the formula, where the subscript I represents a wave number interval of 10 inverse centimeters. ABSI represents the integrated infrared absorbance of the sample in that interval, and FE represents the RF for that interval. Citation needed. The Intergovernmental Panel on Climate Change, IPCC, provides the generally accepted values for GWP, which changed slightly between 1996 and 2001, except for methane, which had its GWP almost doubled. An exact definition of how GWP is calculated is to be found in the IPCC's 2001 Third Assessment Report. 33. The GWP is defined as the ratio of the time-integrated radiative forcing from the instantaneous release of 1 kilogram of a trace substance relative to that of 1 kilogram of a reference gas, where TH is the time horizon over which the calculation is considered. AX is the radiative efficiency due to a unit increase in atmospheric abundance of the substance, that is WM2 kilograms 1, and XT is the time-dependent decay in abundance of the substance following an instantaneous release of it at time t equal to 0. The denominator contains the corresponding quantities for the reference gas, that is CO2. The radiative efficiencies AX and AR are not necessarily constant over time. While the absorption of infrared radiation by many greenhouse gases varies linearly with their abundance, a few important ones display nonlinear behavior for current and likely future abundances, for example, CO2, CH4, and N2O. For those gases, the relative radiative forcing will depend upon abundance and hence upon the future scenario adopted. Since all GWP calculations are a comparison to CO2, which is nonlinear, all GWP values are affected. Assuming otherwise, as is done above, will lead to lower GWPs for other gases than a more detailed approach would. Clarifying this while increasing CO2 has less and less effect on radiative absorption as ppm concentrations rise. More powerful greenhouse gases like methane and nitrous oxide have different thermal absorption frequencies to CO2 that are not filled up, saturated as much as CO2, so rising ppms of these gases are far more significant. Applications. Carbon dioxide equivalent CO2e or CO2eq or CO2e of a quantity of gas is calculated from its GWP. For any gas, it is the mass of CO2 which would warm the Earth as much as the mass of that gas. 34. Thus, it provides a common scale for measuring the climate effects of different gases. It is calculated as GWP multiplied by mass of the other gas. For example, if a gas has GWP of 100, 2 tons of the gas have CO2e of 200 tons, and 9 tons of the gas has CO2e of 900 tons. On a global scale, the warming effects of one or more greenhouse gases in the atmosphere can also be expressed as an equivalent atmospheric concentration of CO2. CO2e can then be the atmospheric concentration of CO2, which would warm the Earth as much as a particular concentration of some other gas or of all gases and aerosols in the atmosphere. For example, CO2e of 500 parts per million would reflect a mix of atmospheric gases which warm the Earth as much as 500 parts per million of CO2 would warm it. 3536 calculation of the equivalent atmospheric concentration of CO2 of an atmospheric greenhouse gas or aerosol is more complex and involves the atmospheric concentrations of those gases, their GWPs, and the ratios of their molar masses to the molar mass of CO2. CO2e calculations depend on the time scale chosen, typically 100 years or 20 years, since gases decay in the atmosphere or are absorbed naturally at different rates. The following units are commonly used. By the UN Climate Change Panel, IPCC, billion metric tons equal to NX 109 tons of CO2 equivalent, GTCO2 EQ39. In industry, million metric tons of carbon dioxide equivalents, MTCD40, and MMTCO2 EQ. For vehicles, grams of carbon dioxide equivalent per mile, GCO2E mile, or per kilometer, GCO2E km4142. For example, the table above shows GWP for methane over 20 years at 86 and nitrous oxide at 289. So emissions of 1 million tons of methane or nitrous oxide are equivalent to emissions of 86 or 289 million tons of carbon dioxide, respectively. Under the Kyoto Protocol, in 1997, the Conference of the Parties standardized international reporting by deciding C Decision Number 2, CP3, that the values of GWP calculated for the IPCC Second Assessment Report were to be used for converting the various greenhouse gas emissions into comparable CO2 equivalents. After some intermediate updates in 2013, this standard was updated by the Warsaw meeting of the UN Framework Convention on Climate Change, UNFCCC, Decision Number 24, CP, to require using a new set of 100-year GWP values. They published these values in Annex 3, and they took them from the IPCC Fourth Assessment Report, which had been published in 2007. Those 2007 estimates are still used for international comparisons through 2020-23. Although the latest research on warming effects has found other values as shown in the tables above. Though recent reports reflect more scientific accuracy, countries and companies continue to use the IPCC Second Assessment Report SAR-17 and IPCC Fourth Assessment Report values for reasons of comparison in their emission reports. The IPCC Fifth Assessment Report has skipped the 500-year values but introduced GWP estimations, including the climate carbon feedback F, with a large amount of uncertainty. Other metrics to compare greenhouse gases. The Global Temperature Change Potential, GTP, is another way to compare gases. While GWP estimates infrared thermal radiation absorbed, GTP estimates the resulting rise in average surface temperature of the world over the next 20, 50, or 100 years caused by a greenhouse gas relative to the temperature rise which the same mass of CO2 would cause. 13. Calculation of GTP requires modeling how the world, especially the oceans, will absorb heat. 25. GTP is published in the same IPCC tables with GWP. Another metric called GWP, pronounced GWP star 45, has been proposed to take better account of short-lived climate pollutants SLCPS such as methane. A permanent increase in the rate of emission of an SLCP has a similar effect to that of a one-time emission of an amount of carbon dioxide because both raise the radiative forcing permanently, or in the case of carbon dioxide, practically permanently since the CO2 stays in the air for a long time. GWP therefore assigns an increase in emission rate of an SLCP, a supposedly equivalent amount tons of CO2. 46, however, GWPPP has been criticized both for its suitability as a metric and for inherent design features which can perpetuate injustices and inequity. Developing countries whose emissions of SLCPs are increasing are penalized, while developed countries, such as Australia or New Zealand, which have steady emissions of SLCPs, are not penalized in this way, though they may be penalized for their emissions of CO2. 47, 48, 45. See also carbon accounting, carbon footprint, emission intensity. References.